So introducing also Benjamin, really nice to have you. Especially, I mean, you did your PhD at KIT in theoretical physics, so it's like really there is also connection to personal momentum on that side. But also excited to hear more. I mean, I think that will be really interesting for everyone also about your experience. You have been a cohort member of Entrepreneurs First in Berlin. You joined Lunar Ventures as an associate and I covered there also Deep Tech, still covering it. From, yeah, I mean, a future of computing to novel materials through AI. So really excited to hear about that. He's also actually the author of a blog, so Future of Computing, same name, interviewing people from the industry. And at the moment, you're tinkering with ideas, startup ideas, what to build and found. So if you have something in the back of your mind, especially in the deep tech space, also, I guess, reach out to Benjamin through LinkedIn. Yeah, you returned from the US. Super interested also to hear more, perhaps about this, if this is also affecting actually, yeah, unbundling of chips. What is the topic today? So really great to have you, Benjamin, and yeah, over to you.
Thanks, Lena. What a wonderful introduction and summary. Yeah, hi everyone. Nice to be here. I've prepared a couple of slides just to have some visuals to give you an overview of the unbundling of chips. Let me show those and then walk you through quickly. And feel free to share questions, ask questions at any time. Let me see. I should probably start this as a slideshow, like this. You can see my screen.
Now it works
still
perfectly.
Okay.
Yeah.
Awesome. Cool. So yeah, the objective of this talk is really to give you an overview of different trends that are ongoing. Like, I won't get into much detail on how all of those work in particular. Like, if you're interested, feel free to ask me. But this is really an overview of where the industry is going and what kind of trends we're observing. And we're observing a fundamental paradigm shift, the unbundling. And unbundling here is, of course, a reference to a very famous quote by Jim Barksdale, the former Netscape CEO. The only way to make money is bundling and unbundling. And so today we'll dive into the latter part, the unbundling. So the unbundling of semiconductors. How did we get here? Now, when semiconductors, so microchips, started out in the early days, they were not as powerful. Like, you started with a few transistors, you had more transistors, and eventually you got quite a bunch of transistors, but those chips were still not powerful enough to do meaningful computations. Like, if you wanted to simulate weather events or other scientific calculations, it was necessary to specialize your chips to the use case. And one early company that was kind of famous was Cray, from a supercomputing company. And they did specialize their CPUs to deal with vector data instead of just scalar data to make it work for scientific computations. And then what happened? We got Moore's law. Moore's law is pretty much this, I mean, it's an observation, but it holds true for a very long time, that every 2 years, the number of transistors on an integrated circuit is doubling. So it's an exponential increase in the number of transistors, and at the same time, an exponential decrease in the cost. And this gives rise to more and more powerful chips. So of course you could specialize your chips, but at a certain point, it was just not worth it, because if you just waited, for another or 2 chip generations, they would be powerful enough to address your use case. So the overhead associated with specializing your chips was just not worth it. And so we got, for the vast majority of use cases, one flavor of chips. Those were CPUs, the good old central processing unit that we all know and love, based on MOSFET transistors. So for a very long time, there used to be more or less just one flavor, bundling all of compute into this one form of CPU. Now, what happened? As time went by, something very fundamental happened in 2005. If you see my LinkedIn post today, you might have wondered what happened in 2005. It's called linear scaling breaking down. So this is another observation, but it held true for a very long time until about 2005, that when you made a transistor smaller, that also its power consumption would go down in proportion. So your overall power density of the chip would stay constant, which is good. I mean, smaller transistors, less power consumption, that's what you want. But the thing is in 2005, this relationship broke. So transistors still got smaller, but their energy consumption and heat dissipation did not reduce in proportion as you would expect. And so Dennard scaling broke, which means heat became a much more severe problem for your microchip. And even today, it's most often not the actual transistor that's the bottleneck for compute, but rather how do you get rid of all the heat that is within your microchip? Or how do you supply data to the microchip that is your memory that is limiting you? So pretty much from 2005 onward, what happened is that we still put more transistors on a microchip, but that happened mostly through parallelization. So, GPUs taking over for scientific compute, going from a handful of CPU cores to literally hundreds, thousands of GPU cores. So we still added more transistors, but they did not get faster. When you look at the actual clock speed of your processor, it's somewhere plateaued around, a few gigahertz, be it 3 or 5, or I guess like top-notch clock speed performance today, if you overclock the latest Intel processors, somewhere around 9 gigahertz. So somewhere in that range, but it did not go to dozens or hundreds of gigahertz. And that's mostly due to heat, because it's just super hard to get all the heat out of your microchip. It's a very severe problem that we somehow need to address. And it's more fundamental than just data center energy consumption. I mean, of course, carbon footprint and data centers consume a lot of energy. That's also a problem. But also a chip level, you need to get rid of all the heat. And that's a severe bottleneck. So what happened then, in addition to, all of those problems with, dealing with heat and getting rid of heat, is AI. Or in practical terms, machine learning, pretty much doing linear algebra. And what happened with AI on the one hand is that AI got super, super valuable. Like AI unlocks use cases that are so valuable that it suddenly became worth it to customize chips just to address AI use cases. While on the other hand, AI in the form of machine learning requires a very different math from general purpose math. Like it's not that you need to compute anything possible, but you need to speed up a certain kind of operation, namely matrix multiplication and linear algebra in general. And those are comparatively simple operations, but you need very, very many of them. When you think of trillion parameter large language models, you need a lot of these operations, and they need to be performed quickly. And so what we're seeing until the recent machine learning hype, the latest, is this further unbundling of chips. So we've been going from one flavor, CPUs, to two flavors, CPUs and GPUs. And now we see all different kinds of flavors popping up and emerging. And yes, other chips like field programmable gate arrays, FPGAs, they've been around before, but they were not as common. The same with ASICs, application-specific integrated circuits. They were not as common, but now, over the past decade, Google and others have really put a lot of effort into engineering custom ASICs for machine learning. And so on the one hand, we see this specialization of chips becoming geared towards machine learning. And on the other hand, people start exploring new principles for computing, such as quantum computing or photonic biological computing. We'll touch on that later, which might give us even more capabilities to address problems that CPUs just can't solve, at least not on a reasonable timescale. So it goes both ways, being more specialized and being more general. But especially we're seeing more and more chips pop up. And so that's why I call it the unbundling. We'll have just many more flavors. Now, how to think about this in terms of structure? I'd say there are about 3 levels of abstraction, how to think about novel chips. One is novel digital chips. So we stay digital, We still deal with zeros and ones, but we think about a better architecture for the use case at hand. For example, Google's tensor processing unit for machine learning, or Grok's chip. Those are still digital, but they're just faster. They're more performant because they're specialized to the use case, that is machine learning. Then, second, we see the comeback of analog computing. So using the absolute value of a physical quantity for computing, and we'll talk about that a lot more. But the key thing here is, despite being analog, this is often used to still speed up traditional maths like linear algebra. Whereas the third level of abstraction is leveraging fundamentally new principles for compute. And I guess the most notable one is quantum computing. Of course, everyone has heard about that, but there's much more. Like there's biological computing, there's neuromorphic computing, there's all of that goes beyond just bits or analog or even running established mathematics. It might be just fundamentally new physics that we leverage for computing. Let's dive in. And feel free, by the way, to interrupt me anytime that you have questions. Otherwise, I'll just keep going. So we stay in familiar territory with digital chips. So we're still zeros and ones. Now, what can we do to make our digital chips more geared towards the job at hand, machine learning? Now, one thing is parallelization. We talked about NVIDIA. Everyone has heard about NVIDIA. We have GPUs. So we have more cores to juggle all of the work. This could be taken even one step further, like the Cerebras, really thinking about what is the largest possible AI chip I could build on a single wafer? Like, can I run an entire AI model on a single chip, on a single wafer, so to say? Whereas most models today, they require several GPUs, several GPU racks. Then there are other startups like Grok also thinking about, okay, maybe I need different memory. Maybe I need on-chip memory rather than high bandwidth memory. Maybe I need a fundamentally different way how I supply this data to the chip. So it's still digital, but it's so fast because it has a different architecture. And then there are, of course, all of those more specialized chips for edge computing. Lattice Semiconductor might not as well known as NVIDIA, but they do low power FPGAs, mostly for edge applications. You know, if you have a drone or a sensor somewhere to evaluate that data, they're becoming big, especially, you know, with the advent of drones and IoT and edge devices. So all of that is still sort of the same familiar computer architecture, which is called the von Neumann architecture, which basically has a separation of memory and processor, and you're shoving data back and forth. And while this was very convenient to design computers, it has become a bottleneck because memory is typically way slower than your processor, which means the actual bottleneck for most of AI compute today is memory and bandwidth to get data from memory into your processor. Now, what you could do about this is in-memory computing, pretty much doing computations within your memory. So you're still digital, but you're computing within your memory. Two companies that pursue this are Accelera AI, the other one being Syntura. And I just picked Syntura as an example. I've interviewed both of them for my Future of Computing blog, and so I picked this one as an example. They're based in Switzerland, and they're designing a new chip for AI, where the idea is really you don't shove this data back and forth between memory and processor, but you do the computation within your memory. So this gives you better energy efficiency in terms of 1 to 2 orders of magnitudes better compared to state of the art. If you consider, say, Apple's neural processing unit as state of the art, this could potentially be 1 or 2 orders of magnitudes better. So there's a quite significant improvement that just comes from avoiding this von Neumann bottleneck, but we're still digital. Now, we could take things even one step further and go into the analog regime. Analog meaning you're using the absolute value of a physical quantity, such as a current, for compute. And so on the one hand, there's analog computing in general, It's seeing a comeback. People explored this previously and then abandoned it just because digital compute, due to Moore's law, just so fast and efficient. But it's seeing a comeback. And one company pioneering that is Anabrit. They're based in Berlin. And what they build is these analog computers. At the moment, they're pretty large and chunky. And they also build these small boards, mostly for educational purposes. But what it does is it solves physics equations, so very complicated differential equations in almost real time. So the idea is, think of, you have an airplane and you need to control the airplane. It needs to be stabilized. So you have lots of mechanics, fluid dynamics, all different kinds of differential equations that you need to solve. Now, what you could do on the one hand is use a digital computer, solve those equations, and feed it back into your control system. Or you could build pretty much an equivalent electronic circuit, that is your analog computer, that is governed by the same equations. I mean, adjusting for some simplifications, but it's pretty much the same maths. So if you solve the analog computer, you solve the actual problem that you're interested in, that is controlling the airplane. And that is pretty much one example. Where the main value add is really being faster in solving, like orders of magnitude faster in solving these very tough differential equations. Now, this is fairly general. You could address different maths, different equations. But one kind of maths, when you think of machine learning that is particularly important, is linear algebra. So there are a bunch of companies specifically focused on analog computing for linear algebra, most notably matrix multiplication. So there's sort of the OG, that's Mythic AI. They've been around for quite some time, but also more recently on the West Coast, there's Mantium Technologies. There is out of Dresden Sembron. There is Genesis out of Aachen. They do training. And also more recently in New York, there's normal computing, which uses probabilistic computing. And the objective of all of those companies, and there are of course many more, is to speed up maths, the matrix multiplication. Just to make this, to illustrate this, I've picked Sembron as one example, based in Germany, just raised funding early on. And so what they do is they pursue this crossbar architecture that is sort of well known for memristors, where you embody a neural network by hardware design. So a neural network, pretty much, it's a matrix. You have different weights and biases, but fundamentally it's a matrix. Now, what you do is you encode this matrix in this crossbar array, where for a memristor setup, you have all resistors here. So you encode the value of your matrix of the neural network in the resistivity of any of those resistors. And then you apply a voltage and it results in a current, and that does pretty much the matrix vector multiplication. Now what Sembron does is to use capacitors instead of resistors. So you go from DC to AC, and that is a lot more energy efficient. Whenever you have resistors, you have resistivity. So you have ohmic losses like heat being generated, versus when you go to AC and use capacitors, you have a lot less losses. And so you get a lot more energy efficient. And I mean, to put these numbers into context, that's like 3 to 4 orders of magnitudes better than state of the art, potentially. Like, think about a system being 10,000 times more energy efficient. That's the power of analog. And of course, there are a bunch of problems along the way. Like, you need to integrate this analog chip now with digital systems. You need to do the digital analog back and forth conversion. There's a bunch of overhead involved with this. But if you make it work, the promise is that this is unparalleled energy efficiency. And this is interesting, not only inherently because you're saving energy, that's obviously good if you save energy, but also because it leads to less heat dissipation. If you remember from early on, clock speed was limited by heat dissipation. Chips today are limited by heat, which means if we get rid of heat, that's good. That's what we want, because it allows to push for higher clock speeds, but also to put different compute layers on top of each other and build genuinely three-dimensional chips. Like, when you read about three-dimensional chips today, most of this stuff refers to three-dimensional transistors, but it's not a three-dimensional chip in the sense that you have different compute layers. It's usually one compute layer and more or less three-dimensional transistors. Whereas what Zemron might attempt to do is to build actually three-dimensional chips, like put 1, 2, 3, 10, maybe hundreds of compute layers on top of each other and stack all of those into the third dimension, which might allow you to run a large language model, when you think of Llama or any of the other more recent ones, on edge, super energy efficiently, like on your smart glasses. That might be sort of the vision of where this might go over the next few years. So analog is super, super exciting, and I could spend way more time on this, but there's still a third level of abstraction that I want to talk about. And that is leveraging novel physics principles for compute. So far, we've used electronics and semiconductors for compute. But the question is, what else is out there that we could use for compute? Maybe we could use photons. Maybe we could use quantum systems. There's actually a very good argument that classical computers using electrons, they're not that powerful. There might be a lot more to it to simulate other systems efficiently. And I guess the most obvious one is quantum computing. And there's a lot of talk about quantum computing. That's why I won't go too much into the details. There are so many companies working on this. But I guess the key thing is really that a quantum computer is more powerful than a classical computer for certain problems. Like there are very specific problems, like prime number factorization, where we know a quantum computer can solve those more efficiently in polynomial time. So going back to a famous David Deutsch quote, asking about whether there are universal computing devices, and whether a classical computer, is universal, the answer is no. And we even don't know if a quantum computer is universal, because, well, this is now getting really into philosophy, but we still don't have a good theory of quantum gravity. We still don't understand what is quantum gravity. And so we don't know if there might be laws down the road where we could use those for computing, and we might have a quantum gravity computer. And that might give us an ability to solve entirely different problems. And if you're interested into this, check out Quantum Country. It's an amazing blog. Now you know that VC stands for very curious. And so if you're very curious, go check out Quantum Country. It's an amazing blog. And I just want to spend just a bit more time on quantum computing to give you one more example. That is quantum brilliance. And I've picked this company because it's not the standard quantum computing company. And I use this to illustrate sort of two directions where quantum computing at the moment is going. So there's one direction that aims for the galaxy brain overall vision of we build large scale fault-tolerant quantum computers. And we'll put them in data centers, we'll cool them down to close to absolute zero, and they will be stationary. So that is one possible direction. It's obviously very hard. We haven't figured it out so far. But those might be the kind of computers to solve prime number factorization. Now, there's a more hands-on approach pioneered by quantum brilliance. And I'm not saying this is any better. It's just different. And it's different in the sense that it's asking the question, what can we do with quantum computers maybe today or in the near term? So we know they're error-prone, they're noisy, they're imperfect. What can we do with them? And the idea there is, okay, it might be just 10% better. We just compete on weight, on dimension, on price. We're actually solving a business problem. So if it's better than a CPU, great. we use it. And yeah, so that's pretty much this divide. And so yeah, that's what I wanted to illustrate. There's a lot more going on in quantum computing. Could talk for hours, but I'll now skip ahead to discuss some other, I would say more under the radar trends where there's still chips leveraging different physics. One is biological computing, where Cortical Labs, a startup out of Melbourne, Australia, they're using actual neurons, like neurons from mice in a petri dish and to program them to solve computational problems, especially for robotics and real-time computing. This might be interesting. And they're, integrating these neurons with AWS and other online clouds. So you can send your job to the neuron and it does the computation. Then there are also spiking neural networks, which on the one hand could be different hardware, but primarily is a different machine learning algorithm and philosophy. Now, neural networks, what you have today, those are continuously differentiable functions. So one neuron is feeding into the other one, and you use backpropagation to train the neural network. And you can do that specifically because it's continuously differentiable. Now, that's not how our brain works. Our brain is a mass of neurons, and beyond a certain threshold, these neurons fire. But it's not continuous, and it's not differentiable. It's actually more like a spike train. And spiking neural networks try to emulate that dynamics with either code or hardware. Oftentimes hardware, what Inotera is doing for Edge and SpinCloud is sort of doing for data centers and Edge. And they're building hardware to use these spike trains, like a fundamentally different way to do AI. That might be interesting for robotics, but it's also inherently interesting because you add a time scale to the problem. Like a normal neural network, it has no time scale. Like inputs go in, outputs come out, there's no time scale. Whereas a spiking neural network has an internal time scale of when a neuron fires, when the next neuron fires, how long the spike takes. It can process temporal dynamics, which makes it fundamentally different and exciting. The last trend that I want to talk about is photonic computing, which honestly, in some regards, might be much more exciting, or at least much more near-term than quantum computing, in the sense that over the next 5 to 10 years, I would say a large part of the data center shifts to all optical. And the reason being that it's just more energy efficient. There's nothing faster than light. You never get any lower latency. And different light colors don't interfere with each other, which means you could use lasers with different light colors for compute, and you can parallelize with the number of colors, which is pretty convenient. You don't need to parallelize with more cores. You just add more colors. Now, what's going on in photonic computing is that we had this first wave of compute startups. Light Matter, Lightelligence, both out of Boston, Salience Labs out of the UK, Celestial AI, where all of those looked into AI accelerators. So again, making linear algebra faster with photons. Now, fast forward a few years, and we learned that in principle, that's a good idea. But in terms of practical implementation, that's pretty hard because you need to integrate your fast AI processor with very slow legacy electronic systems. And the back and forth conversion between electronic and photonic signals just kills it. Too much overhead. So what we're now seeing is sort of the second wave of photonic compute startups, where on the one hand, existing players like Light Matter or Celestial, they've raised just recently new rounds of funding, and they sort of pivoted into short-range data communications. Because again, when you think about AI, one of the core bottlenecks is getting data from the memory into the processor. So you need to overcome this von Neumann bottleneck, where you either do something fancy like in-memory computing, or you brute force it, and you have a photonic link that is just faster and higher bandwidth to get data from the memory into the main processor. So there are these, so to say, incumbents, like 5-year-old incumbents, looking into short-range data communications. But there are also newer companies like Encoden out of Paris. They're building nanolasers to literally beam information from one chiplet to the other. So short-range data communications, short-range, like not fiber, but kilometers between data centers, but short-range really rack to rack, chiplet to chiplet, like from centimeter to millimeter and micrometer scale. That's what we're going to see. And what we're also going to see as part of the second wave of computing startups is very specialized logic compute functionalities, such as firewalls, such as network routers, such as digital signal processing, DSP, which is what New Photonics is looking into, or Ecotonics out of Munich, looking into logical photonic chips in general. Now, why would you do this? The key insight there is to prolong the path that information travels optically, because you have information already today traveling optically between data centers through a fiber cable. So it goes optically into the data center, and now what? You want to prolong this path as long as possible to avoid this back and forth conversion between photonic and electronic signals. And that's when you address the firewall and the network router and all of those other components. And step by step, I would predict a large part of the data center will eventually switch to all optical. Just down the road, it's much more efficient. But it's again a cold start problem where you need to find the first use case that's valuable, because you're competing with hyper-optimized ASICs with billions, potentially trillions of transistors that are still quite powerful. So you need to make it work somehow. Now, this has been, a lot. I know, so many trends, and I left out all the details. But if you'd like to know more, I'm writing this blog that Lena mentioned about the future of computing. Been doing this for the past 2 years, interviewing more than 100 startups. And if you're curious about the startups and recent trends, feel free to check out futureofcomputing.com. And if you have any more questions, feel free to ping me by email or on LinkedIn, or just now, with, I guess, still plenty of time. And yeah, happy to chat.
Thank you so much, Benjamin. That was a great overview, and I'm sure there are a lot of questions. So yeah, I mean, does anyone already want to start? Is there any open question out there? Yeah, Andy, you go.
My time to ask the proper VC question. What is your heuristic when you're looking at a new chip startup, like whether this is a VC case or this is just kind of nice fancy research that maybe someone can commercialize, but maybe not the unicorn type?
Yeah. I guess that's the multi-billion-dollar question. And if you knew, you would obviously start a fund and make use of that knowledge. It's tricky because, Mythic sounded very promising, right? As in, they pretty much do something similar to these memristors. When you think of Simron, this crossbar memristor architecture, they do something very similar, and they've been doing it for years. And it's all sort of reasonable, like you get very good energy efficiency. So it should be good. Like, machine learning is important. So why has Mythic gone bankrupt and just got revived recently? There are many things that you need to consider when integrating with existing ecosystems. Like, I guess that is one of the key insights that one might learn from the failure of this first wave of photonic computing startups, the failure of Mythic and all of those others. Integration is a bitch, so you somehow need to solve this part to make your chip work with existing legacy infrastructure. And the other part is, that's also very important, you need to be able to program your chip. So it's not just looking at the hardware level, but it's also thinking, how will people actually program for my chip? And that's where NVIDIA has a stronghold on GPUs, because they have CUDA, and so they can juggle those workflows across GPU cores. But it was also one of the key insights of Grok, for example. So this company here, that was started by the ex-Google tensor processing unit guy. So he left Google, typical Silicon Valley argument. We don't want any single company to develop AGI, so let's do it ourselves. And he founded Grok starting with the software. So they actually built the compiler first, and then they built the hardware around the compiler, and to make it work both ways. And now they can offer their own Grok cloud, and they can control the whole thing end to end. And so I guess one of the key insights there is really a benchmark of being faster as a processor is not enough. You need to think how to integrate, how to program it, and how much of the bottleneck does it actually solve? Just one more example. When you think of speeding up linear algebra, how much of a bottleneck is that in machine learning? Now, it's a certain part, right? You need to do all these matrix multiplications. But the thing is, you still need to get your data from the memory into the processor. And that's where a lot of those companies also fall down, or at least memory is a severe bottleneck. Honestly, I think memory is under-indexed. And if you find a good company that does on-chip, like SRAM memory, or even better, develops optical memory, this might be very, very interesting, especially optical memory. At the moment, we have no good way to store and access data at light speed because you can't really store light on its own. And so you need to think about something more sophisticated. So your memory is not lagging behind your photonic processor. And yeah, I could go on, but I guess those are just a few bits and pieces I would think about.
Awesome, thanks.
Yeah, then Mike, do you want to go next? Not sure, I
Oh,
can't
you're still
hear you.
muted.
Yeah.
Very good point. Unmute really helps. Two questions. First one is the analog thing, right? Like if you think about that, couldn't we just basically ditch like everything to analog stuff, or what are the limitations of that?
The limitations, I mean, near term are in the digital analog conversion. And then the other limitation is accuracy, because usually analog systems excel at providing very quick answers and solutions to an equation, but it might not be the most accurate solution. So if you require a certain bit level precision, like you need an answer, significant to 8 bits, that might be a challenge. And that is also one of the key, insights or contrarian bets behind Semron, and probably also some other startups. Because most people at the moment, like when you think of those in-memory computing guys, etc., Centura, what they will tell you is analog computing does not work. Why? Because you can't hit the required accuracy level. You can't get to 8 bits, let alone 16 bits. Maybe you get to 6. Now, that's why they do in-memory computing, but they stay digital. But the contrarian view to that is put forward by Semron, where they say, no, wait, we found a way. We can manage that. We will get to 8-bit accuracy, and we'll see. I think they will make it work.
Okay. And the second question was regarding spiking neural networks, right? As far as my understanding goes, the backpropagation is really the really cool thing, right? That really made all AI actually work, right? There's really the special thing that the stuff is differentiable and this speeds up the learning process. Now we go to spiking neural networks. What will replace backpropagation there to learn fast?
Yeah, that's an excellent question.
Okay.
Why? Because it's one of the core problems of why spiking neural networks didn't work in the past. Because what you would do, formally, is you have a conventional neural network, and you would sort of adapt it to work as a spiking neural network. And this works, more or less, but not quite. Now, there's been a new research paper, I think like 3 years ago, published by researchers in Heidelberg, that found a better way to estimate gradients in a spiking neural network, because the core problem is your spike train is discontinuous, so you cannot differentiate it. Now, if you find a way to smoothen out the spike and to still get a faithful representation of your gradient of the network, you can actually do backpropagation, but you need to be smart about it. And I think thanks to this breakthrough, and it seems to be a breakthrough, at least when I've talked to the Spin Cloud people, and they said it's been transformative. Like now we can train spiking neural networks, and it seems to be going forward not to be an issue anymore.
That's interesting.
Thank you so much also for that nerd talk. Whoever didn't understand everything at the moment, super fine. Don't feel bad. Really, I'm with you. Handing over to Nima. You got a question for us.
Hi, first of all, thanks for the very interesting talk. Just one question on your take on hybrid models. I mean, sometimes maybe accuracy is not the most important thing when you're like doing a calculation and you're rather on the like let's do it like very fast and efficient. And you can use, for example, analog chips, or like different kind of applications. So what is your take here? Will we see like computers with like many different types of chips where like one intelligent operating system is saying, okay, now we use this kind of chip or this kind of chip?
Yes, exactly. So when we go back to the very first slide, you still have a CPU. There are even startups today working on better CPUs, and I think that has a certain justification because we still need to explore new algorithms in general, and we don't want to constrain our search space of all the possible things that we might want to do. That's why even optimizing CPUs is still valuable. But then, yes, in the future, we will have way more chips in any given system, in a data center, possibly also on edge devices. I mean, on edge, you're always constrained by space and by energy, so you really need to see what trade-offs you're making. But in general, I guess that's a core theme of the unbundling part. You will have more chips and more specialized chips for different functionalities. Some of them might be digital, some might be photonic, some might be analog.
Super interesting. Philip, I don't know if your question is still valid. If so, feel free to speak up.
Yeah, maybe might be also more philosophical question. When you let's say highlighted all these different avenues, I thought back like 70s and 80s when BNR basically released SL1 and fought against, let's say, what Bell Labs released, and ultimately they won because of they were faster and the use case back then was better. And as you also highlighted here, it's more about the use case than specifically, and because you also highlight here CPUs and Kropotkin releasing 1-bit, let's say 1-bit implementation of very deep learning structures. Do you think that we will reach use cases where these applications ultimately will succeed against CPUs or chips as we have them today, and also new standards being established such as RISC-V and ARM, like doesn't matter, but against the constant evolution of the chip as we know it today?
Yeah, totally. Like in short, yes. In the sense that, yeah, we'll have many more chips for different use cases, and some will hyper optimize, on edge to detect the cat or the drone or whatever you like to detect super, super efficiently. Well, on the other hand, we will have very, very powerful data centers, much more powerful than today. And one thing that I've not talked about, and which is rarely talked about, which is also very interesting, is that compute might as well become reversible. And this is sort of early stage research, but if we get energy consumption down to a certain level, there's still a fundamental limit on how much energy gets produced by just gates and algorithms being irreversible. And if we somehow manage to make reversible computing work, we might even drop, a couple orders of magnitude below that level. In other words, we become freaking energy efficient. What this might allow you to do is, on the one hand, to have these always-on AI devices where you don't need a battery anymore, you don't need a socket, you might need just a condensator, and you have always-on AI devices pretty much everywhere. Dozens, hundreds of them. Well, on the other hand, being so energy efficient, you could not only stack compute layers on top of each other, you could build entire computers as large, not just buildings, but entire cities, entire planets. You could build a planet-sized computer and ask about the question of life. Check whether it's 42. Like, when I'm saying the future will be amazing in the sense that we will have very, very different compute chips, all the way from being super tiny, all the way to being super large.
Maybe a follow-up question, which is, or not a follow-up question, but unrelated question, because we talk about energy efficiency and being, let's say, pinnacle there, and always heat, like being limited by heat. Even though we have active cooling, why is nobody investigating something like heat recovery systems as part of, let's say, data centers or large computers? I'm sure there are, let's say, some POCs where you build or like data centers around that, but is there no scalable solution to basically cover that use case? And if not, why?
Let me put it this way. There's a certain problem to remove heat at the data center level, but it's not that much of a problem. I mean, it's a problem in the sense that it costs you a lot and it produces carbon emissions, and all of those are unpleasant, but it does not fundamentally limit you. That's why people put data centers in Texas or Nevada, where it does not make sense from a heat perspective, but you can still cool those down. I've even talked to one company a while back. They use machine learning to operate all the parts within a data center to know, okay, now I need to cool it down. Now I need to vent some compartment. Now I need to do this or that. So I would say that part is manageable. And I mean, you can reuse heat. I mean, also for commercial real estate or just households. There are different ways to deal with heat on a data center level. What is much more intricate and severe is to deal with heat on a chip level, because you need to get the heat out of the chip, which is hard. Now, there are many chips using air, but air has only so much heat carrying capacity or heat conductance. So if you want to go really high power, you need some sort of fluid. Now, fluids don't drive well with electronics, so you have a fundamental problem there to keep everything under control. But yes, the most advanced chips, they are cooled with liquids. And there are a couple cool startups. One example is Corinthus. They map out the heat distribution of a given chip, and then they design a cooling system specifically for that chip. And you get these very cool looking fractal structures that really account for that very heat distribution of that very chip. It's cool. And maybe one last thing on that, people are looking into diamonds for chip cooling, because diamonds have one of the largest heat conductivities. So it's really good to either have just a diamond layer on top. It's way more efficient than having a fluid, to just get the heat out of the chip, and then you get it out of the data center. Or, I mean, in the future, some fancy future, you could build entire chips out of diamonds. Like, not for every use case, it's pretty expensive, but for some use cases, it might be worth it.
Actually, one of my questions is related to this one. Like, is there, or what are the fields you would love founders to focus more on, or where would you like to see more startups actually being built? And also connected to this, are there areas that are totally overhyped where you say, oh, I see so many startups in that field, and actually please don't go into that direction anymore in the chip universe?
Yes. Very good question. In the sense that I guess the AI application layer is terribly overhyped. And so it's sort of the AI chip market. I mean, you have some early, wouldn't say winners, but promising companies like Grok. So I wouldn't necessarily start the next Grok at this point in time. And also, from a geopolitical perspective, a lot of the chip manufacturing capability is either in Taiwan or, it will be in the US, but it's not in Europe. So if we, want to be sovereign and you want to develop something fundamentally new, it should be new. Like, for example, a new photonic chip. I really admire what Photonics is doing. Going out there into the wild, exploring logical photonic chips and just seeing how you could build a firewall or how you could make it work for high frequency trading. So I guess photonic computing, especially an insight on how to make it work. I guess that's a key thing also for analog and neuromorphic computing. Some key insight on how to make it work. Why does the back and forth conversion from digital to analog, from electronic to photonic, why is it worth it? If you have some insight there, this could be very valuable and one avenue forward where you're then, I mean, obviously everyone wants to be CMOS compatible and wants to, work with TSMC, but eventually we'll need to build our own fabs in Europe, and they might not compete with TSMC. They might be for photonic chips, and they might work entirely differently from current fabs. So I guess that is one part. The other part is memory. Like I mentioned this before, but I really think memory is under-indexed. If you have a good insight on how to optimize on-chip memory, SRAM, or if you have an insight how to build quantum memory, because we need to transfer quantum data more efficiently. I mean, there's Wheeling out of Paris looking into this, but you know, I guess one or a few companies is still not enough. How to store and access photonic information, access information at light speed. Like if you have a good insight on how to make memory work, that would be very, very cool. Something I would look into. And then basically, just fundamentally for AI, the question is, what systems can we use for intelligence, to be intelligent? And we've learned that there are these neural network algorithms, and, you know, we have the feed-forward architecture, the neuron, and sort of it's a nonlinear system that appears to be intelligent if we train it. But what we fundamentally need is a nonlinear system, where you have input parameters, you have a nonlinear system, and then it sort of splits these input parameters in a high-dimensional space, so you can separate them. And that's what we call AI. Now, if there's a way to do the separation in a different way, this would be very interesting, especially if it's very energy efficient. And so there's one domain that I've not talked about, but that is very much related to my own PhD research, that is called reservoir computing. And I guess no one is really looking into this at the moment, but it's really this idea of using physical systems, in this case, magnetic systems, for compute. What I did for my PhD, I mean, it was pure fundamental theoretical physics, but I was modeling magnetic materials. And those magnetic materials are doing all sorts of cool things. They do spin spirals. They do other topological structures that look like a hedgehog called skyrmions. They do funny things. And fundamentally, all of those are nonlinear. Like for example, you apply a voltage and the current that's generated, it's fundamentally nonlinear as a relationship. So people use those magnetic systems as a reservoir for AI, where people have done a benchmark. You do spoken digit recognition. So someone says, oh, 1, 2, 3, etc. Now I have a conventional neural network running on a digital chip, and you have a magnetic system that was trained to discern all those numbers. And now you run inference in this scenario. And both get to sort of the same accuracy level, like 95, 97%. It's not hyper optimized, but it's okay. It's a starting point. It's research. But the thing is, the reservoir system gets by with about 3 to 4 orders of magnitude less energy. So again, we're saving energy, and this could be super, super interesting for edge AI. And so it's very much research stage, but any insight on how to harvest intelligence, you know, it doesn't have to be a conventional neural network. Other systems can be intelligent too. What might it be? Some insight there might be very valuable.
Thank you so much, Benjamin. I mean, if you don't have an idea now, by now, where to build something in, then I guess, yeah, text Benjamin. He has plentiful. Thank you so much, really, for the super interesting talk. I think it was really enjoyable, really technical, and but still broken down to a level that everyone could relate to. Thank you so much for this overview. As we're already at 7 p.m., I would suggest whoever is up for like a quick breakout rooms, 10 more minutes. If you have 10 more minutes, just stay in. For all the others, thanks for joining so much. Looking forward also to the next session next month, actually with prequel. So yeah, stay tuned there. And again, thank you, Benjamin, so much for coming in and joining.
Sure, my pleasure.